Are you building applications that query datasets with filters and paging? Well, my goal in this video is to show you some designs that I have for caching datasets and how I'm incorporating that in my own ASP.NET Core application. So before jumping over to Visual Studio and going through code, I just want to talk about some high-level concepts that should hopefully align us on what we're trying to accomplish here, and then hopefully that will make the code a little bit more easy to navigate. When we're trying to scale up applications, one of the things that we have to be concerned about at some point is that if we're running a lot of queries to hit a database, that can be something that's really expensive. And it's expensive because of the round-trip time to go from your application to your database to get those results back. Depending on the types of data you have, of course, this could be still pretty fast, or you might find that with more user load and more queries running, that this becomes a bottleneck in your application. So, of course, you're going to want to do some benchmarking before going overkill, trying to cache things and optimize, but let's assume that you've done some of that work. You're finding that your database and your filtering and paging is becoming a bit of a bottleneck, then hopefully what we're going to talk about will make a lot more sense and be a lot more applicable. So in this video, I'm going to talk about a result set cache. I've touched on this a little bit in a previous video, which I will link above, and I didn't get into the design of the result set cache. I got into the design of the other caching components with sort of a tiered architecture. But in this, we're just going to focus on the result sets being cached. So what do I mean by a result set? Well, if we consider a filter that's being run on a set of data, and I'm trying to be generic here, but to be more specific, we could say like a particular query that we want to run on a MySQL database, for example, and it has like an offset and a limit, so you're doing some paging as well. What we want to be able to do is be able to snapshot the results that come back, and then the next time we go to run that query, instead of running the query, we can actually check our cache and say, hey, look, we have a filter that actually matches this. We have a cache of that filter, and we can return that data from either memory or some other type of cache. Again, going back to that multi-tiered cache idea, instead of going to the database and running the query again. So effectively, we can short circuit going to the database. Now, a couple of things that we have to keep in mind is that when we're thinking about caching this kind of stuff, one, we can't just go store everything in memory. And potentially in your case, if your data sets are small, then maybe you can. In my case, I have at least one type of data set that has, I think, approximately 2 million records, and there's no way that I can pull that all back into memory. So for me, I have to be able to do paging for my users, but I also have to consider how much I can store in memory when it comes to the results of the filters that I'm running. So the one limitation is going to be the memory limit. If we are caching things in memory, even if you're using Redis, it's going to be memory somewhere. The other constraint that we have to navigate around is that, at least in my application design, you can request pages technically out of order. So this is going to mean that if we have a filter that's running, let's assume that the total set of results that can come back is 100,000. Maybe the first person to run that filter, we know there's 100,000 records, but what's actually happening is they're requesting the first 100 items in that 100,000. There's nothing to stop the application from allowing paging to go, say, get records 300 to 400 of the 100,000. And technically that process can keep taking place to, if you're thinking about it kind of as like a bucket filling up, to go keep getting these different segments and filling up that potential 100,000. But going back to the first point, I don't even know if I can store 100,000 records in memory. So the constraints kind of put together will mean that we have some concept of being able to pull in pages, potentially out of order, and we have a limit to how many pieces of those pages we can actually fit into memory. So the class that we're going to be looking at is my design for a result set cache, and I guess one more point that I want to make is that the result set cache itself is responsible for mapping a filter with sort of some page constraints, so an offset and a limit, or like a page size. And then the other part to that cache, so it's a filter mapped to the IDs of the records, and then there's another part to the cache that actually has IDs mapped to the entities as well. So we are kind of separating the concerns of how you're going to cache your entities with just the filters with a paging mechanism mapped to the IDs of those records. So that's my preamble. Let's jump over to the code, and if you stay right till the end, I'll have another video where I walk through why unit tests were super applicable for me in this scenario and how they made my life a lot easier in ensuring that this class was working as expected. All right, I'm here in Visual Studio and I have my result set class pulled up here. And the first thing we're going to notice is that a result set is composed of result set pages, which I will show you next. So it can have multiple pages in it, and we must know the total count of items for the filter that we're running. And this is going to be an important mechanism for us to actually understand and make optimizations about how we consume this data by knowing that there is a full result set pulled into memory here. So a way to think about this is that we would have one contiguous page. So this read-only list would have one item in it with a number of IDs that match the total count for filter if it's a full result set. And that's what this property here actually demonstrates for us, right? So one page, and that single page has all of the IDs for that filter. In theory, you could have multiple pages, and if you were to sum them, the IDs should match up. But the way that this class is designed is that it will merge the pages such that there is only one by the time that we want to have a full result set loaded into memory. I'll come back to this method after. I just want to go jump to the result set page first. So the result set page is extremely simple. If you recall what I was saying previously, when we're talking about result sets for these filters that are running, we're actually just going to be tracking the IDs for the entities that we're interested in. And you'll notice that this is really very simple. It's generic. I'm not requiring a specific type of ID here. This class or this record doesn't actually care at all. It's just going to have a list of IDs, and it's also going to have an offset. There's just a couple of other convenience properties here, and this is really just to help give it this feeling that it is a page, right? So if we have an offset, having this end index, we're going to have a count, which is truly just the IDs collection, the count of that. So just a couple of convenience things added onto here so that when we're reading through the algorithms that consume this, it's just a little bit more easy to understand. If I jump back to the result set record that we have here, I'm just going to walk through this other piece. It's called try get page, and try to explain how, given a result set, how we'd be able to pull back a particular page defined by the offset and the page size here. And something interesting that I just like to call out is that the logic for this method is going to basically try to interpret this offset and page size and figure out how that aligns to the data that's currently pulled in based on the pages we have. And this method will only be able to return true if we were able to get the page based on the constraints that were passed into here. So for example, if you recall what I was saying at the beginning, we can technically have multiple pages of IDs pulled in, right? And they don't have to be contiguous. So if a full result set, before it's merged into the single page, if before that happens, it was actually a total of, let's say, 10 different pages of data. Let's assume each page was, say, 100 records, and there's 1,000 in total, so there's 10 pages that would make up the full result set. If we only had 3 of those pages loaded, for example, and someone was requesting a particular offset and a page size that we did not have access to, then this particular method would return false. It's trying to suggest, hey, look, based on this cache that we have, we don't have the page that you're asking for, so you're going to have to go get it for yourself. So with that said, let's expand this and check out what's happening inside of here. I just have a couple of different contracts at the top here that kind of enforce that we have the right parameters passed in, like the right ranges of things. So that's all that we're seeing right here at the top. If a particular page size being requested is less than 1, then we're basically saying, like, you're not asking for anything. So no, if you're asking for that, we're not giving you anything back. It seems like it's a little bit of an invalid input, but based on my design, I was just saying, like, if you're looking for something less than 1, then I'm just going to say it's empty. So next, we're going to talk about this full set optimization that we have here. I do have a fix me because I am not totally sure yet if I know the optimization I want to make here, so I'll touch on this in just a moment. But if we have a full result set, and if you recall, a full result set is going to mean that we have one single page that has all of the IDs for that filter that we wanted to run. And if we're looking at this next condition here, someone is basically saying, give me from 0, so start at the beginning, and give me as much as possible. So this is actually, you could make an assumption here that this should say, double equal, so exactly the full set. Then we just give you back the full set from the cache. However, there's a couple of instances in my code where I'm not respecting the page size. So I might say, like, give me from offset 0 to int.max, right? That might be a ridiculous page to go ask for, but the implication of that, or the expectation as the caller is like, hey, just give me everything that you possibly can. So if everything you possibly can essentially maps to give me the full result set for the filter, then in my opinion, that was a good match for just give me the full result set. And instead of failing it for going over the limits, it's just telling the caller, like, whatever you're asking for, like, this is truly the limit of it, and it's everything that matches the record set for that filter. The other thing that I just want to call out is that if anyone's asking for a page and we have the full set, I left this fix me here because I think there's probably some other optimization where I could do like basically pages, like take the first and only page because it is a full result set. I could probably do something like a skip. So skip the offset, take the page size, right? So I could use something like link here and then return that. I have not actually tried that out. When I get into the unit testing video, which will follow this one, that might be something that we could explore together in that. But for now, I've just left this here because all of this is supposed to be an optimization to avoid the database. And right now, this didn't seem to be something that was, causing an issue to not have this optimization in place. Let's go a little bit lower here. Some of what you're seeing on the screen so far is really just kind of setting up this algorithm. And essentially, without getting into all of the details, because it's not super important here, this part of the algorithm is just going to be responsible for essentially building up a list of IDs that we want to pass back that match the particular page that we're trying to get out. And the only reason that this becomes a little bit more complicated than just a very simple for loop or a for each loop is just the fact that we have to walk over multiple pages to be able to potentially pull back that set that the caller is asking for. So that's what this particular piece does. It's just trying to map the existing pages to that range. And you can see that we end up adding those pieces right here. And you can also see that there is this concept of skip and take. So like I said, something like this line here, line 68, probably, if I scroll back up, probably applies to here on the single page scenario for the full result set. So probably we'll revisit that. Next, this last part here is just looking at whether or not we can return that page. So did we end up getting to a situation that's going to meet the expectations of what the caller was asking for? That's what this will do. And then this debug assert is just because on top of the unit tests I explained in other videos that when I write tests, it's to build confidence. And for me, this type of logic where I am mapping bounds of different pieces to a new set of records, this type of thing is something that always, historically, I've been programming for like 20 years now, and this type of algorithm where I'm looking at different bounds and mapping them between different things always messes me up. So this is just an extra layer of confidence so that when I'm running things, if I happen to miss testing scenarios, that this would help basically catch things at runtime and when I'm debugging. So in particular, this last line that I have highlighted on line 84 here, this is actually a debug assert that I added because there was a weird situation, and by having this line in here when I was exercising some more complicated filtering, I actually ran into this issue. So this was actually really helpful just as a stopgap. And that's mostly it for this result set class that we have, but a result set on its own is not the full picture. So I mentioned at the beginning that the purpose of these result sets is to map filters to these result sets, right? So we're going to have a filter that we can go run on something like a MySQL database or whatever, whatever your backend is. We're going to go run a filter on that, and then we want to map that filter to the result set. And that way we can have a cache that says, if I'm running this filter again, do I have results that I can just go look up from the cache? So the next thing we're going to go look at is actually this result set cache class. So we'll start from the top. The result set cache is going to be generic again because we're only interested in caching the particular IDs. And it's using this iCache layer, and I will link another video in the top of this so that you can go see that, because that's where I'm talking about my multi-tiered cache. So for what it's worth, if you don't go watch that video, and that's okay, this iCache layer is just a concept that I have where it's a facade, and it could be an in-memory cache, it could be a distributed cache, or it could be multiple layers of those caches. So just an interface for caching. I'm just going to collapse these methods so we can see what's available. And what we have on the result set cache is to be able to set the things in the cache for a particular key and given a page, which is also going to require the total count. And that's a very important part, like I mentioned, because this particular piece of information will let us know if we have a full result set pulled into the cache. And that's where a bunch of those optimizations came in. The other piece that we have on here is really just trying to pull out a result set given a cache key. So you'll notice that on this particular class, even though I've been talking about running filters, you might say, hey, Nick, I don't see anything about filters on here. And that's right. And it's because this iCache key, I'm allowing the caller to basically decide how they would like to map a particular filter to a cache key. For me, I'm able to take the hash code of the filters that I'm running. So my filters are basically just data transfer objects, DTOs, that describe the constraints, like the conditions, anding them together, ORing them together, doing inverse operations. They're just DTOs, and if I get the hash code of that, it should give me a unique enough cache key to be able to go work with this. But however someone else might want to implement a cache key, this is really just left to be a little bit generic for that reason. So let's go look at the set method. Again, just a little contract at the top to double check for errors. You can see that the first piece we have here is checking if we have a full result set. So if we do, we're just going to remove whatever we have in the cache, because if you recall, we could have had in particular, like disjoint pages already loaded in. So we're just going to say, whatever's there, forget it, right? Forget what's there, and we're just going to go set that whole new result set to be the total new set of IDs that are pulled in. So this is basically that situation where we're saying, hey, look, we got everything we need, and don't worry about what's there right now because we can override that. Otherwise, what we need to go do is get to see if there's already a result set for this cache key. And then from there, what we want to do is actually basically add in a new entry if we don't have one, right? So if we go to ask the current cache, do you have a result set for this? And it says no, then no worries. We'll just add in what we got. So this is a pretty simple case here. And then the final part is the more complicated one. And I don't necessarily need to go walk through the algorithm here, but essentially what it's going to do is try to insert the page into the cache if we need to go modify an existing result set. So that's what this does here. And then this last part, this is a little bit messy, and it's kind of funny because as I'm creating this video, there's probably, if I spent more time walking through the details of exactly what this does, either myself explaining it or someone watching this might go, Nick, this is not optimal. There's a way better way for you to merge these things, and I'm not going to sit here and pretend like I optimize this to be, fewest allocations possible or fewest iterations. Certainly not claiming that. But this is something, again, going back to me writing unit tests around this, this is something that was working. And now that I have tests in place, if I need to go tune this for performance, I can always come back and try to optimize it. But just to collapse this for a moment so I can show you kind of the overall algorithm at the end here, what I'm doing is inserting a page into the full set and then double checking, like, do I have any overlapping ranges in my result set? If so, start merging them together. And if you recall what I said a little bit earlier, this is the part that's going to ensure that my result set, if I have a full result set pulled into memory, will always just end up having one single page. So this enforces that if I had 1,000 IDs in total that matched a filter, and each page was 100 in terms of size, then I'm not going to have 10 pages pulled in, each with 100 records. I will just end up getting one single page with all 1,000 by the time this is done running. Then at the end, we just set that into the cache. The next part here is just to try and get the things out of the cache. And what's awesome about that is it's just asking the cache. There's no complicated algorithm here. And that really just summarizes the two operations that we can perform on this cache. All right, so that is the implementation of my result set cache. I understand that walking through that code might be a little bit complicated, especially because I'm just talking about it because I've already written it and you're not kind of sitting there kind of designing it with me. So I tried to go through at a pace where if you need to go rewind it and kind of watch over other parts, hopefully it comes across clearly. But just to quickly summarize what was covered, the idea was that we have result set caches that will take a filter, and we didn't look at the filters being run. That's an entirely separate thing. You can implement that however you would like, and it's agnostic to whatever sort of data backend you're working with. And the idea is that given some filter that's going to map to a cache key, that's up for you to figure out how you'd like to do that. Given that filter, we're going to have a set of IDs that match the results of that filter. And we're also going to take into account the paging, so filter and paging. From there, we're able to store the IDs that map to that filter and those pages, and the classes that we looked at actually take into account managing the paging, allowing you to pull out other sub-pages from there and work with optimizations on a full result set that has been pulled into memory. One of the optimizations really requires that you have a full count of that filter. So for example, if your filter was going to match 10 million records from your data set, I'm not suggesting you pull in 10 million records into your result set cache. Probably not a good idea. But knowing that your result set does have a full 10 million, you can actually have optimizations or the opposite, right? Like you can't take advantage of some shortcuts and optimizations if you do not have the full set of IDs actually pulled in. So I just wanted to like double down on that part because when I was designing this, a lot of the challenges I was coming across, like the gotcha scenarios, were that I did not have the count available. So I had to go change my application when I'm running queries. So I actually have to go have a cache miss, go hit MySQL. I have to go double up on queries now. So one is going to be to pull back the page of IDs that I'm needing for my result set, the filter that's being run. But I also have to go pull back the count of potential records that map to that filter. So 2 queries, so the cache miss becomes more expensive, but when this caching is in place, it ends up being so much faster. And I think in general, this is an approach I've used before in production, and I wanted to apply it here in my own projects. So I hope that this was valuable. I think that if you're going to try implementing something like paging and result sets for your filters, if you have a different approach, I'd love to hear about it in the comments because I think that this is a really interesting space for optimizations. So hopefully that was useful, and thanks for staying right to the end, because if you watch this video here, you can see how I tried to unit test this and why that was really valuable for me. So thanks for watching. We'll see you next time.